All right, the last lesson in our unit on exponents and exponential functions will be on geometric sequences. This will be related to what we learned about with arithmetic sequences earlier in the year. So we'll learn how to write an equation for a geometric sequence and see how it's related to exponential functions. So geometric sequence, it's a sequence when the ratio of any term to the previous term is constant. That's known as the common ratio. So remember, arithmetic sequence is when we had a common difference, when we added or subtracted a similar amount. Here we have to have a common ratio. So for instance, 3 to 6 to 9 to 12 to 15. Here each time we're adding 3. And when we add 3 each time, that's a linear pattern. That would be an arithmetic sequence. And the next term of this one would be plus 3 more would be 18. Here 128 to 64 to 32 to 16 to 8. The next one would be 4. And you can see that we are multiplying by a half each time. That would be an exponential pattern. So this would be a geometric sequence. Geometric is when we are multiplying by a common ratio each time. Okay. So hopefully you remember the difference there between arithmetic and geometric. Arithmetic, we have common difference. Geometric, common ratio. So let's plot these points and see what happens. So this is our first term, second term, third term, fourth term, and fifth term. So we label the first term, second term, third, fourth, and fifth, and our x. Y will be our values. So our first term is 128, second term is 64, third term is 32, fourth is 16, and our fifth term is 8. We graph those points on our graph, and you can see that exponential curve coming into play there. So if I were to connect those, I can see my curve going on there. Is this a function? Yes, it's a function. Each input has an output. It's like an exponential function. Common ratio, I can see that I'm multiplying by a half each time. So the equation, we would talk about what would our equation be. Well, if this were an exponential function, I would say y equals a times b to the x. Y equals a. It's my initial value. Well, my initial value would be way up here at, this would be at 256 if we went back another point. So 256 times a half to the power of x. So notice we can write that in that format. I'll show you the recursive and explicit forms of the geometric sequence and how we work that. But keep in mind, when we have a geometric sequence, we're starting with the first term. So it's not going to be totally like our a times b to the x, because we're always starting with the first term. So notice to get to the fourth term, I multiply by our ratio only 3 times. To get to our third term, I multiply twice. To get to the nth term, I multiply by r n minus 1 times. So that's where we get our equation, similar to y equals a times b to the x. So our nth term is equal to the first term times the ratio to the n minus 1. So a times b to the n minus 1. So this is our explicit formula. Recursive formula, a recursive equation. Just like in arithmetic sequence, we're just going to take our nth term is equal to the previous term, a n minus 1, times our ratio. So whatever the common ratio is. So it's just describing what's happening each time. So let's look at the example we had in example 1. What was that? 120. Look back again. 128, 64, 32, 16, 8. Okay, so let's go through the list and find out our rules. So let's just consider the recursive rule. So what's going on here? Well, we know that our common ratio, and maybe we should write our common ratio down first. Move this down a little bit. So our common ratio is a half, because that's what I'm multiplying by each time. So my recursive rule would be a sub n equals a sub n minus 1 times a half. So the nth term is equal to the previous term times a half. Okay, so the explicit rule, we're going to start off with our first term. So a1. So the nth term is equal to the first term, which is 128, times our ratio, which is a half, to the n minus 1. Make that a little bit neater here. 1/2 to the n minus 1, because we multiply 1 less than the term number. So to find the 10th term, I can plug that into my explicit formula. 128 times a half to the 9th power. And then I could just evaluate that equation. So I can go onto my calculator and evaluate it. 128 times 1/2 to the 9th power. Oops, forgot a parenthesis there. So times 1/2 to the 9th power gives me a value of 0.25, or 1/4. So the 10th term would be 1/4. That's how we find that. So we're basically applying what we know about exponential functions, but using it in the context of a sequence. So let's take a look at some of these examples here and write the equations for those. First of all, tell if they're arithmetic or geometric. So I want you to check with yourself. Try these first 6. Tell if it's arithmetic or geometric. We don't need to graph it right now. But just look at the differences or ratios and find out if it's arithmetic or geometric. Restart the video when you're ready. Alright, so as we can see, we have the first one is geometric because we're multiplying by 4 each time. Number 2 is arithmetic, we're adding by 9. 3 is also arithmetic, adding -6 each time. 4 is geometric, multiplying by an eighth. 5 is geometric, multiplying by -2. Notice they alternate between positive and negative. And number 6, adding 14, so that would be arithmetic. Let's take a look at 7, 8, and 9 now and write the rule, the explicit rule for the nth term. And then let's find a sub 7, the 7th term. Pause it and restart it when you're ready to check it out. So number 7, the nth term equals 1 times -5 to the n minus 1. So that gives us a value of 15,625 for the 7th term. Number 8, we're multiplying by 2 each time. The first term is 13, so 13 times 2 to the n minus 1, which means the 7th term would be 832. 9, we're dividing by 6, or multiplying by 1/6 each time. First term is 432, so 432 times 1/6 to the n minus 1 gives a value of about 0.009. Let's finish up by taking a look at number 10. Chain email instructs recipient to forward the email to 4 more people. Maybe you've gotten something like that before, which asks you to forward something on to X number of people. Well, you can see how it quickly reaches a lot of people if everyone follows the pattern. So the first person sends out an email. They send that to 4 people. Those 4 send it to 4 people. Those 4 send it to 4. So we're multiplying by 4 each time the number of people that receive emails. If they each send it on to 4 more people, we can see it increasing exponentially. So let's take a look at, first of all, the rules for that. So let's just take a look at the recursive rule. Well, the nth term is equal to the previous term times 4. Explicit rule will state that I'm starting with the first term, which is 1, starting with 1 person. They send it to 4 people, so multiply by 4 to the n minus 1. So the first 6 terms, well, the 5th term, multiply the previous times 4. 64 times 4 would be 256. And after the 6th round of emails, we'd be up to 1,024 people would have received it. So that's how we can continue that pattern by using the recursive formula. And we could set up the explicit formula and say, well, in the sixth term, we would have 1 times 4 to the fifth. 4 to the fifth is 1024. So it confirms what we got with the recursive. Recursive is good for finding the next step in the pattern in the sequence. Explicit works better when we want to find a term that's further down the sequence. So as you can see, it connects directly to what we learned with the exponential functions, and hopefully connects well to what you learned already with arithmetic sequences. So you'll do some of that in your practice today.